Let us determine the shear flow values and plot shear flow distribution and locate shear center distance for the given beam section with booms. The given beam section is subjected to an external shear load of 141.14 kilonewton, which is acting at an angle of 45 degree with respect to the horizontal. With respect to the horizontal. This is the shear flow expression for open section. So the inclined shear force can be resolved into two components, a sax 141.14 cos 45, 100 kilonewton acting right side positive, and 141.14 kilonewton sine 45, 100 kilonewton act approximately acting upward positive. Okay, so we have to locate the centroidal axis. To locate that, we need to find x bar and y bar. So x bar is equal to sigma ax by sigma a. Taking B, stringent B as a reference, stringent B as reference, area, stringent area into x distance, 312.5 into 400 plus 312.5 into 400 divided by sum of the area of all stringers, which gives 133.33 millimeter location of the y axis from stringer B. Then y bar, sigma ay by sigma a. Let B be the reference. This is 625 into 300 area into y distance plus 312.5 into 200 divided by sum of all the areas, which gives you 133.33 millimeter to y bar, the location of x axis above the stringer B. Hence we have located the centroid. Now Ixx sigma a y square, the formula. Okay, area. Y is nothing but the vertical distance from the stringer, respective stringer to the x axis. Stringer area into y square plus stringer area into y square plus this stringer C area into y square plus stringer D area into y square. So if you simplify, you'll get this. Okay, so y value is positive above x-axis and negative below x-axis. So you get this 35.42 into 10 power 6 mm power 4. Iy sigma a x square. X is nothing but the horizontal distance of the respective stringer from the y axis. Okay, so it's stringer A area into x square, stringer B area into x square, plus stringer C area into x square, plus stringer D area into x square. So x value becomes negative when it is left side of y axis and positive when it is right side of y axis. So when you simplify, you get 66.66 into 10 power 6 mm power 4. Then product moment of inertia Ixy is equal to sigma axy area into x distance into y distance. X is nothing but the horizontal location from the centroid to the respective stringer. Y is the vertical distance from the centroid to the respective stringer. Stringer A, x distance, y distance. Stringer B, x distance, y distance. Stringer C, x distance, y distance. Stringer D, x distance, y distance. Or directly you can take the x distance, y distance from the Ixx and Iyy. You can see here, okay, x distance for the respective stringers. You can write as it is x distance. And y distance you can get it from here for the respective stringers. You can take the values from here itself directly. So you get minus 8.33 into 10 power 6 mm power 4. Now substitute Ixx, Iyy, Ixy, Sy, Sx in this equation. So you'll be substituting all the values here and here also. You'll get the shear flow expression in terms of xdA and yda for the given section, which is valid for the given section. So this is the expression. So the shear flow expression also where have xdA, yda. dA is nothing but area of the stringer. So if you want to calculate the shear flow between stringer AB, we know that very well. The shear flow between the booms always remains constant. So QAB or QA to B remains constant. Okay. X is nothing but horizontal distance of stringer A from the centroid. and y is the vertical distance from the centroid A to the stringer A. From the centroid to the stringer A. dA is nothing but area of the stringer A, like this. Okay, 625 into x distance into y distance. Okay, that is y distance. Okay, so you can see here minus 0.0019. Okay, x distance, sorry, area, stringer area 625 into x distance minus 0.0033, y distance y distance 166.667 into area 625. You can see here, right? So this is y distance and this is x distance. You got this minus 185.42 Newton per millimeter. Now QBC, carry over the previous shear flow value as it is, and this equation minus 0.0019 into B now. Stringer B you have to consider. Stringer B, okay. So stringer B, this is the x distance for stringer B, and this is the y distance, and this is the area. Okay, substitute here. Okay, you get 247.91 Newton per millimeter. And QAB is minus, you can see here A to be 185.42 anti-clockwise minus, and QBC is plus clockwise. Okay, BC is clockwise, positive. CD carry over the previous value. So write to the equation again. Stringer C, x distance, y distance, and the area is 312.5. 312.5. Substituting that, after simplification, you get 227.07 Newton per millimeter plus. So it's clockwise. How to locate the shear center? Let us assume that the load is acting at a distance E from stringer B. Let us take moment with respect to this stringer B. Sigma MB is equal to 0. And this 141.14 kilonewton, you can convert to Newton, you can see here, into E anti-clockwise, negative. And when you take it to the other side of the equal sign, it becomes positive. So this is the shear flow, 227.07 multiplied by this length, it becomes a shear force into perpendicular distance, which becomes the moment. And this 185.42 QAB shear flow, it gives anti-clockwise, so minus. Whenever you write down the moment equation for a curved web, the formula you have to use is 2AQ. 2AQ. So 2A is nothing but, so for stringer AB, I'm writing the moment equation. B is my reference point. You just connect this by a dotted line. So this becomes the area. Okay. So 2, this area is pi r square by 2 into Q, shear flow 185.42. So this shear center is 35.84 millimeter. So the 141.14 kilonewton shear load is acting at a distance of 35.84 millimeter from stringer B at an angle. Load is at an angle of 45 degree. Thank you.